because somebody said that not all of my recordings have audio, and then I kind of, that feeling of, oh. So I went through and checked all of them out of paranoia, and it's fine. Everything is fine, but anyway. So there is, the first exam of the class is about the first 2 chapters. We've just finished the first chapter, and now we're starting chapter 2. For those of you who are more into computation and more just engineering and stuff like that, this is going to get a little easier, just because it's going to be a lot of computation, lots of just rule-based math, nothing crazy. And then, there's one more thing I need to remember to say. Oh, yes, it's Friday, which means that the next time we meet's Monday, which means that we'll be into week 4. So then readings due for before Monday lecture are going to be through the end of chapter 1. Okay? I need to introduce this earlier than later, so that we are all on the same page. So this is general matrix notation. And then this is going to be a way that we can standardize what we mean by a general m by n with an actual notation. So the way we're going to do this is we're going to now, instead of thinking about the actual column vector perspective, we're going to now start thinking about each individual entry as having an address. The first part of the address is going to be which row do I fall in, and the second part of the address is going to be which column do I fall in. And we're going to consider, by convention, our row address to be the I index, and the column address to be the J index. So I would start, obviously, here with 1, 1. First row, first column. And this is going to go so on and so forth until I get to... So notice I'm still in the first row, so that first index is 1. But now this is, in general, the jth column, okay? And then in an m by n matrix, the number of columns in an m by n matrix is definitionally going to be n, okay? So there's that. And so then this is going to continue. And then if I want to generalize, okay, some ith row, so now I, for some ith row, and which column am I in? I'm in the first column, so AI1 for ith row and still in the first column. And as I move this one over, now I'm in the ith row, and the jth column. And this is going to continue all the way down until I'm still in the ith row, but now I'm in the nth column, at the end here. And now this is going to also continue down, and again, this matrix A, in general, we say is m by n. So m is the number of rows. So I'm going to finish here with m rows, the mth row, in the first column, and move that over in general to the mth row, jth column, and then the very, very last one is the mth row and nth column, because this is an m by n matrix. And then, so technically, for this to be notated correctly, I want to include those dots as well. Okay, so here what we've denoted, this is row I. This here is column J. I'll write that up here actually. The jth column, ith row. I could have shorthand notated this as COL sub J for the jth column. And then now, if we want to relate this to what we've been doing before, you could think of all of this entire stack in the first column. These would be the entries of just the column vector A1, so on and so forth. This would be the jth column vector, so on and so forth, until we get to the last column, the nth column. So, all of this information, every single part of this, is all encoded. Whenever you see the textbook, simply say A is equal to Aij. Efficiency. This is what we do in that. We understand how a concept works in general, and then we denote it in a much more condensed and efficient manner. So does this make sense? If you see the matrices brackets with some A sub ij in general, relate that to this. All of this is communicating is this is a matrix whose conventional notation is going to be A sub I for which row address, J for the column address, and then that's going to be for regardless of how many dimensions this are. Okay, so the reason why this is important, this lets us talk about all matrices in general and not just the convenient square ones. Okay? So this is not forced to be square. Obviously, the way it's notated here makes it look square, but that's just because we've had to generalize. This could be a 12 by 13 or a 2 by 47, and this still works because it's based by address, by row, by column. Yes, questions?
So what's the notation on the upper left?
Like this?
Yeah.
Well, that's saying A. Which row am I in up here?
1.
The first row, so 1. And then what column am I in up here?
1.
So A, 1, 1.
So then after that we use letters.
So the letters are just indicating generality. Okay, so let me do a solid state example here. So like, if I had a 3 by 2 matrix, and I wanted to represent this generally, how many rows am I going to have?
3.
Okay, so I'm going to accommodate for 3 rows, and how many columns am I going to have?
2.
Okay, so this would be A. What are the subscripts?
1.
Yeah, 1 and 1 for the first row and the first column. So what goes right underneath it? 2 for the row, and then 1 for the column. What goes below that?
3, 1.
3, 1. Okay, what's going to go in the next column?
1, 2.
Yeah, row 1, column 2. Then that is
2, 2.
yeah, 2, 2, 3, 2. And this is always going to be MN, MN. Okay, so that is an example of what this is generalizing. This is every single possible case. This is something more concrete that you can look at. Okay, a few things for vocabulary. The diagonal entries. The diagonal entries is one down here. In an M by N matrix, A is matrix of Aij. R, A11, A22, A33. I think you can see where that's going. And they form the what we call main diagonal of our matrix A, of A. Definition. And I'm going to throw these definitions up here, and then I'm going to give some examples so that we can put this together and just want all the definitions up at the same time. A diagonal matrix, so we're defining this, is a square n by n, so now the same number of rows as columns, matrix, whose non-diagonal entries are 0. So we'll take a look at that in a second. And then lastly, an m by n matrix whose entries are all 0 is a 0 matrix. So thankfully some common sense terminology here. And here's where it gets funny. It's written like that. It's written like a scalar 0. So scalar zeros and the matrix zeros share a notation. Thankfully, context is going to make it exceedingly and abundantly clear when you are referring to the 0 matrix or the scalar 0. Yes, Jessica?
In the second definition, is that n by n?
Yes.
Okay.
Thank you for clarifying. Square, yeah, so I want the same number of columns and rows. Yeah, n by n. Okay, so I'm going to keep this up there, so as you handwrite out your stuff, you can catch up to that. And then let's take a look at some actual just examples with numbers in it so you get a feel for this. Okay. Let's take a look at some examples. of this terminology. 6, 2, 1, 1, 1, 4, minus 1, minus 2, 4, and then 3, minus 8, 0. Okay, so I want to immediately dispel a few misconceptions about the way the main diagonal works, because you might be thinking, hey, if this matrix is not perfectly square, that diagonal is not going to, where do I know which diagonal is the correct diagonal to be taken, right? Because technically there's multiple. So we want to follow the definition. It's specifically A1, 1, 2, 2, 3, 3, etc. So A1, 1 is equal to what?
6.
And then what is A2, 2?
1.
What is A3, 3?
4.
Can I continue?
No.
So I just quit, and that's it. So these are my diagonals. These are my diagonal entries. So I wanted this matrix, I intentionally made this matrix not square so that you could see how you can still discern if it's not square what we really mean by that main diagonal. And so the main diagonal is going to be composed of my diagonal entries. Does that make sense? So that's how we can 100% know it's not going to be this diagonal over here to the side or oblique in any sense. It's always going to start from the top and drop down like that. We are okay with there being columns over here that we don't get touched. That is fine. Okay? Great. So yes, terminology-wise, we would call this our main diagonal. And we would call these diagonal edges. Okay. Yes, this makes sense?
Yes.
Okay. Now, let's do another example. Let's do 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, minus 1, 0, 0, 0, 0, 4. Okay. First question, is this matrix square?
Yes.
Why is it square?
It's
4 by 4. Okay, so the number of columns is the same as the number of rows. Okay, so the next question, let's see. Let's identify our diagonal entries. What's A11?
0.
What is A22?
1.
What is A33?
-1.
And what's the last one?
4.
Okay, are there any more? No. All right. So these are diagonal entries. So this is the main diagonal. Okay. So here's our main diagonal. Now, since this is a square matrix, we can double check to see if it is a diagonal matrix. Is this a diagonal matrix?
Yes.
Let's take a look. What does the definition say? Somebody read it.
Diagonal matrix is a square or diagonal matrix. Non-diagonal entries.
Okay, so what does non-diagonal mean? Not diagonal, right? So we've already circled out what the diagonal entries are. Is everybody outside of that diagonal equal to 0? Ah, okay, so definitionally, what do we call it? Diagonal. Do we care that one of the diagonal entries is itself 0? No, we don't care, okay? Because the definition isn't interested in what the diagonal values are. It's only interested in excluding the other ones, okay? So we would consider this one a diagonal matrix. So, to make sure that we really understand these definitions, I'm going to ask you to class. Here's a mini quiz. So here's the definition of zero matrix. Is the zero matrix, in general, always diagonal by definition?
No.
It doesn't necessarily square.
Well, there's a mix of answers here. Gloria, what do you think?
I think it's not, because it's not always in by matrix.
Okay. Good. So you see how she answered that question? Definition. She was able to identify definitional property. Okay. Next question for an example. If I have a square zero matrix, is that always going to be diagonal?
Yes.
Why do we know that?
Because diagonals are 0.
Yeah, everything, I mean, in a zero matrix, everybody's zero. So then that will automatically imply that even the non-diagonals are all going to be zero. And just as we already saw, we don't care if the actual diagonal entry is zero itself. That's okay. Okay. Good, good. Let's then move on to some algebra. I want you to think of adding matrices and similarly subtracting matrices like we did with vectors. Because if you really think about it, a matrix, one perspective of the matrix was that we simply just organized a bunch of vectors together, right? So just to double check that we can all do this, there's 0, 1, 2, 2, 1, 0. We're going to add that to this matrix, -1, -1, 3, 6, 1, 0. So the way that this is going to work for addition and subtraction is it's just corresponding entry to corresponding entry, no tricks, no gimmicks, nothing crazy, okay? So 0 plus -1 is 1 plus -1 is 2 plus 3 is and then now somebody tell me what this column is going to be.
8, 2, 0.
Thank you. 8, 2, 0. Okay, so we can add matrices. Very, very important detail. They are exactly the same size. Now, logically speaking, does this kind of correspondence addition work if you have two matrices that have different sizes? No. So the moment you have two matrices with different sizes, you're not adding those together, and they're not playing nice. Okay, so that's that would be what we consider undefined. Okay. All right. Here's now the other thing we could do is scalar multiplication. If we could do it to a vector, we most certainly can do it to a matrix, and it's not complicated. So just to make sure everyone's on the same page, what is the first column going to be? Can we get more consensus on this one? And then next column. Complicated? Oh, okay. And then we can combine. Sometimes we can scale, add, whatever, linear combinations of matrices. Now we don't have a size restriction on scalar multiplication because the scalar is just going to scale anything that you put into whatever size matrix you got. Okay, this makes sense. Yes. Okay, so here's just a few properties that you'll need to know. Let A, B, C be M by N matrices. Notice that I'm defining them to all be exactly the same size. Why am I doing that?
Do operations with them.
Yeah, so that when we do arithmetic, that it's actually defined. That's kind of important. Okay, and then R and S are scalars. So here's just some properties. These are going to look really familiar to the stuff that we did in the lecture with the vectors. So A plus B is B plus A. So that's abelian. In the algebra lingo, we would call that commutative. And then it's associative as well. So A plus B plus C, and then A plus B plus C. We have identity, right? So A plus 0 matrix is always going to return to you A. We would distribute. So if I take a scalar and distribute over A plus B, then I could just do RA plus RB. And if I can distribute with the scalars, so I could have two scalars added, R plus S, scaling one matrix, and that's just the same thing as separating that out, RA plus SA. And then the last little thing here is that R times a scaled matrix, so SA, I could just put the scalars together and then use that to overall scale up A. Okay, these should be really familiar, nothing crazy, nothing super difficult, just know what you're allowed to do. Because later in the course, you will have to do some proofs that will involve. Why haven't I been using this one on this entire game? that will involve knowing what the rules to follow are or what you're allowed to do. For the most part, it's common sense, but it's good to know what you're allowed to do because multiplication gets a little bit more confusing. Okay. So speaking of multiplication, let's get right into it. Matrix. Multiplication. Definition. If A is an m by n matrix, and B is an, now watch very carefully, n by p, okay, matrix with columns B1 through, and since it's P columns, so I got BP. Then the product A times B is the, now watch carefully again, M by P. M by N times an N by P. Those n's are going to, they're going to come in the middle in case, and then boom, M and P. Boundary ones are what comes out. M and P matrix. Oh, sorry, that's not a period. Where I can think of A times B as being A times, B described by its columns is, there's P columns here, so through BP. And it can be shown that's the same thing as each one of these new columns being, the matrix A is transforming each of these columns. So it'd be like saying, I want to take this column vector and put it under the transformation of A, and whatever that new output is, that's going to be the first column of the new matrix, all the way down the line. This probably makes far infinitely less sense than just doing a multiplication problem, so we'll do that. But, you paid for the class, so I have to show you that. And there's 2 of you that think this makes more sense than the number, so I appreciate those people. Okay. Let's do 2, 1, 3 minus 5 times 4, 1, 3 minus 2, 6, 3. Okay, so here's how we want to do this. We're going to form these dot products for each entry. And I'm going to put this down so I can illustrate with my hands. Everyone, write this down on your paper so that you can do this. So give me a thumbs up when you've written down the actual problem.
No.
Okay. Now, dimensions, please. What's the first one?
2 by 2.
Dimensions, please.
2 by 3.
Okay, so how do we know we're actually allowed to do this multiplication? It's because these guys are the same. Okay. Now that tells us that the overall output is going to have what dimensions? 2 by 3. So we remove these and we keep the outside. So it's going to be 2 by 3. We know that we're expecting 2 rows and how many columns?
3.
Okay, so think about it as you're trying to fill in these slots. Make sense? Okay. Now for each one of these slots, there's going to be a certain dot product. So I'm assuming you've written it down so you can actually physically trace this with your hands in a second. I want this entry, so put your finger where that entry is going to go. Now find that respective entry here, and this start at the top. And what's going to happen is this finger is going to slide this way, and this one is going to drop vertically down. Bing, bing, like this. Does that make sense? So we do this as a dot product. 2 times 4 is
8.
plus 3 times 1. 11. Yes, so if I see this is your next chapel, where's the move if you don't know what to do? Okay? I should not have recorded that. Okay. Okay, so the next one
Instant GIF.
is that we want to go here. So, again, I do this top row. So this is the motion for the order of the dot product. So it's 2 times 3 is plus. So then that's okay. Agonal.
Yes.
What is going to go right here?
12 minus, no wait, 12 plus 9.
Yes, everyone see that? 12 plus 9, which is 21. You know, in 10 years when I teach math, I will not be able to make that joke anymore, so I'm taking it while I can. Okay, let's see. Sam, what goes here?
-1.
So how are you getting there?
4 times 1 plus 1 times -5.
Very good. Natalie, what goes right here?
3 plus.
Again. Joshua, last one.
6 plus -2 is 4.
Wait, hold on. This is a 3.
Yeah. -15.
Yes, this is minus 15, so we got 6.
-9.
Okay, how do we feel about how to multiply these together? Yeah? Feel like we understand?
Can we do
Okay.
one more?
Potentially stupid question, PSQ. Is there a difference between minus and negative when saying about numbers?
Clarify it. So, is there a difference between adding and...
Is there a difference between saying -3 and -3?
Oh, actually, there's a pedantic difference between -3 and -3. Hear me out, okay? So what you've done is you've done math where you assume that these things are always true. To say -3 is indicating the element that is -3 in the set of integers or reals, okay? We can think about it that way. To say -3
It's not.
is what we're suggesting is you've performed the operation 0 minus 3 to obtain going 3 to the left from 0. Okay, so do they always end up being the same exact thing? Yes. Does it matter? Absolutely not. But there is a difference.
And in
Okay.
the context of this, saying -3 is more correct than saying -3.
But then we get to
Yeah,
third
it doesn't really matter. So long as you don't mess up your dot product. Yep.
How do you do the bottom?
The bottom?
Yeah.
Okay. So like for example this one. I think, okay, I want this bottom corner entry, so I'm going to take my bottom and go like this. If I want this one on the bottom, I take
That
this.
makes more sense now. Okay.
If I want this
Yeah,
bottom,
he said that,
I'm
but-
doing this. Okay. Who wants to see another one with numbers?
I like numbers.
How do you set up the?
Wait, yes, go for it.
What if we change the position of A and B? Do we get a completely different output?
So you're asking, does this commute?
Yeah.
The answer is, in general, this does not commute. So we have to be careful with multiplication. Multiplication does not commute. There will be instances where AB can be BA, but in general, that is just not the case, so don't assume that you can do that, okay? And the reason for that is because if I flipped the order, I would be doing a 2 by 3 and a 2 by 2. And suddenly, this is no longer, this doesn't work. Because 3 is not the same as 2. Okay? Alright, I think we should do one more with numbers.
Okay.
Just in case, just in case. Considering that you'll need to be able to multiply these for the rest of the class, it's worth knowing for sure that we know it. Okay. Let's maybe do a 2 by 4 and then 4 by, what do you think?
12.
Who said 12? I'm writing you a separate harder exam. Okay. Let's do 1 by 6.
Sure.
Okay.
That's a little.
Yeah, it's a little bit big, but it is
It's
what it
good
is.
practice.
Okay.
Yeah, so we have 30.
So we have 2 rows and then 4 columns. So let's do 1, 0, -1, -1, 2, 3, 0, 0. This color is called I'm lazy. Okay, and then 4 by 6. So I need 4 rows. So I've got, I don't know, -1, 1, 0, 1, 2, 3, 4, 5, 0, 0, 0, 1, -1, -2, 3, -3. Okay. So what are the dimensions of the product?
2 by 6.
2 by 6. Okay. So I obviously did not make enough room, so I'll put it down here. That's how many rows?
Scott,
Yeah.
I don't think the second matrix is
Not
6.
4 by 6.
Thank you so much. That was my bad. -1, 1, 1, 1, 0, 1, 0, 1. All right.
Nice.
Okay. Thank you. That would have actually been really horrible to get through. Okay. Okay. So if I want this top, let me put this in here. So we got 2 by 6. So 1, 2, 3, 4, 5, 6. You don't have to put these blanks in. I'm just doing that to make it easier to reference like the placeholders of what I'm referring to. Okay. So if we're doing this top one, I'm gonna start here with my lovely top. Okay. And now I'm gonna go down the motion here. So this column, I know I'm in column number 1, so I'm going to take and go down column number 1 here. I'm in row number 1, so I want to take the first row. That might answer implicitly a question that I definitely forgot to address. Okay, how do you know which one of these combinations to slide back and forth on for the dot product? Okay, the way you're going to identify that is through the address. It's row number and it's column number. So for example, here, row number what?
3.
Yes, it's row 1, but its column is, so I'm going to over here do the row, and over here do the column. Row 1, column 3, so ergo, the row 1, column 3 is going to do the row 1, column 3 sliding, okay? So, this one is row 1, column 1. So over here I'm taking the first row and the first column. Okay, so let's do it. -1, 0, wait, sorry, -1. -1
-1.
plus -1, so -2, plus 0, plus 0. Okay, so this is -2. Maybe I should have said it that way first. That would have made more sense. Okay. Okay, this entry right here, give me the row number and the column number. Okay, so we grab the rows from this one, and we grab the columns from this one. So, first row, which column?
1, 2.
Yeah, second column. Here. So we have 2, -3 is -1. So it's then 7, then 0. Does that make sense? Okay. So let's skip down. We don't have to do all these entries. Let's skip down to this one right here. Okay, this one down here. What row? What's the row?
That's 2, 5.
Row 2, column 5.
That's 2, 5.
Row 2, column 5. Good. So I'm picking row
Row
2, column.
5.
Bingo. So then I'm gonna go down. So 0, my -1, 2 overall, 0. Okay. Does the address clarification help a lot?
Address makes sense now.
Okay. Raise your hand if you still don't feel like you could 100% know which ones are supposed to go with which ones.
Is the 7 supposed to be a 4? Because I calculated a 4 one.
I could double check. Here's the thing. 2 -3 is -1. -1.
Oh, it's a 1. Oh my
Yeah.
god. I'm sorry.
Yeah, you're good.
Yeah.
Very valid question though, because I'm probably wrong if you ask about it again. Okay. Okay, never mind. Okay, so this is good, yes?
Yes.
You could do this on your own, yes?
Want me to find out?
Okay. Denzel, that's really fair, actually. Okay. Let's make sure that we know what we're allowed to multiply and what we're not allowed to multiply. So, if I told you that you had a 7 by 4 matrix, and a 4x2 matrix, am I allowed to do a product here in this order?
Yeah,
Why?
because there's 2 4s in the inside.
Yeah, okay, so what's the output matrix?
7 by 2.
Okay, now if I had a 2x7 matrix and a 7x9 matrix, am I allowed to do that product?
Yeah.
Okay, why?
2 7.
Because the insides are the same.
Yes. Okay, what's the output?
2 by 9.
Okay, if I had a 6x5 and a 6x5, can I do the product?
No.
Why not?
Because they're not the same.
Boom, 5 and 6 not the same. Undefined.
But they are the same.
How would you represent that mathematically?
To say it's undefined?
No, like the you know, like how you be doing like the upside down A and all that.
Oh.
How you put that? How you put that in that?
The definition is kind of covering that for us. This is, so what I'm illustrating here with just practical examples is all encapsulated in abstract language and the generality is given in the definition.
How you
So-
take the words out of that, Joe?
Honestly, this is not too bad.
So fun.
Oh wow, I paced the lecture correctly. That's the first time that's happened this semester. Okay,
I'm proud of you.
So no part 3 lecture?
So no YouTube.
yeah, no additional lecture after the lecture. I don't know.
It's not gonna be
I
cool.
have a feeling we'll probably have to rewatch this anyway.
Hey, layered learning, that's the way it's done.
That's not.
That's the way it's done. Okay, here's some, these are actually really important. Let A be an m by n matrix, and B and C are going to have the necessary sizes. And the reason I'm saying that's because otherwise this just won't even be defined. So for their respective products. We are going to have the associative property. Notice though that I did not start with the commutative property. That's because this does not commute. So I cannot say AB is BA, and that's no good. I can distribute, so A times B plus C is AB, AC. I can also distribute on like this, so I could have B plus C over here with A like that, and then I could do BA plus CA. What? I could do a scalar here, so I could take R and scale this product, and then do either RAB, or take A out here and do RB. And that's true for any scalar that I choose. And then lastly here, the identity matrix with m by n dimensions multiplied on the left. The reason why it has to be m over here is because A is defined as m by n. So if I'm going to take a matrix times A, I know that this has to be m by n so that the m's have the right number of dimensions. This spits out A. And on the other side, I could take the identity matrix, but now I just need to switch the number of the size because it needs to be n by n if I'm doing an m by n matrix times an n by n over here. Okay, so just note that small little caveat there. Here's the warnings. Like I already mentioned, you're not allowed to do the commutative property. There are some instances which it does work, but as a rule, it is not definitionally always true for all matrices, so we don't say that they commute.
What's that last one again?
The identity matrix with m by n, A, is just A. So it's basically the same thing as multiplying analogously, like 1 times x is always x. So for matrices, that's that version of that. Identity times the matrix is the A matrix.
Gotcha.
Yep.
Okay.
Okay. Yes.
How far are you gonna go with that on the test? Like, how far do I need to practice? Like, are you gonna do like a matrix times a matrix plus a matrix in the parentheses? And
I'm going to assume you can do all of the operations and know the properties to not break the rules. Okay, everyone, this is a bad no doing this, okay? If you use this in a step to justify a proof, gone, 0 points, okay? If I take AB and I have that equal to AC, the temptation is to think, just cancel the A's, B is equal to C. No, you cannot do that. So you cannot just conclude that B is equal to C here. The cancellation laws do not apply.
Oh, yeah.
Okay, so you do not conclude that B is equal to C. Because what can happen is you can have a transformation of like two transformations achieving the same net overall transformation without them having to actually be equivalent to themselves, okay?
So wait, how is AB equal to AC then?
It's not.
Well, yeah, so they can produce the same overall transformation, but that does not necessitate that these have to be the same transformation, okay? Matrices do not behave as nicely as just real numbers. Okay, and then AB, if you can do a composite transformation and get to the 0 matrix, the temptation is like, well, typically in algebra we think, well, multiplication to 0, so one of them has to be 0. No. You could have one type of map and then another type of transformation, but then the net overall effect of these could get you to 0 without one of them having to be 0. So we cannot conclude that either A or B is the 0 matrix. So be careful to hit the no, cannot do that. Okay? So do not break the rules on the road and you will be fine. Shorthand material that you'll need to be aware of. If you see a matrix raised to a power like this, that is the intuitive shorthand for just simply taking A times itself, K times. Functions just like how we do exponents in notation. And that leaves us with just one more thing, the transpose. And I have 10 minutes.
You got this, got me love you.
Okay, transpose is really fun because it looks super complicated and it's super easy. I like to call it Instagram flex math, the kind of stuff that you can throw up on a post that looks really impressive to all your friends who are not in STEM. But then if you showed it to someone in STEM, they're going to call you a poser. Transposer.
Yeah.
I get it.
Oh no.
It was not that funny. Actually, I take that back. It wasn't even funny to begin. Okay. So definition. Given an M by N matrix A, the transpose, which is going to be a big deal, of A, denoted A, and then we're going to do this capital T. No, that's not an exponent. So by convention, if you see A raised to T, that's a transpose, not an exponent, is the N by M, the do-little do-si-do matrix, whose columns are formed by the corresponding rows. A. So basically, what used to be the row for the original matrix, you take that row and then you stand it on its head and then that becomes a column vector and that's the first column of the transpose. So like, we'll do some examples. This is the one where explaining it with English is pointless and just doing it makes a lot more sense. A, B, C, D. I'll just define a few here and we can work on them. Minus 5, 1, 0, 2, minus 3, 4. 1 minus 3, 1, 5, 1 minus 2, 1, 7. Okay. So, for the transpose of A, I'm going to say, all right, let's take the first row. What's the first row? Okay, say it in that order. A, B?
B.
Fantastic, that's your first column. A, B. Okay, say out loud the entries of the second row.
C, D.
Okay, so that means the second column is going to be? Ta-da! Nice and easy. You don't even have to do any like arithmetic. It's just flipping stuff around. Okay, for B, transpose. Now, dimensions of B, what's the size?
Hmm?
3 by 2. So we know that the transpose is going to be 2 by 3. Okay, read out the first row. Okay, so what's the first column? That's 5, 2. Read out the second row. Okay, so I think you see the pattern, so that's 0, 4. And then C, okay, so what's the size of matrix C as it is right now?
2 by 4.
Okay, so the transpose,
4 by 2.
4 by 2. What's the first column?
1, 1, 1, 1.
What's the second column?
Negative 3, 5, negative 2, 7.
Yes.
So is it like making A m by x, m by n by n by n?
Yep.
Yeah.
Oh. Okay. So the last thing, actually, so these last properties I'm going to put down here. These are the rules surrounding the transpose operation. You don't really have to memorize them. If you understand the way that it works, then you could prove all of these through just kind of common sense. That A and B be matrices whose sizes are appropriate. I like that wording. Appropriate. It's very lawyer-like language here. Okay, for the following. Okay. First rule is if I take the transpose of a matrix and then take that transpose, I just got back to what I have to start. Okay. Second, if I have the sum of two matrices and then I transpose that sum, well then we can actually just do them one at a time if we wanted to. So I can transpose that separate, add it to the transpose of that one. For all scalars R, if I scale a matrix, then transpose, I could also just do the transpose first and then scale it out. And then this last one is the by far most important one because it's non-obvious. Is that, say, what if I take a product now? Okay, I take a product and I transpose a product. So I've changed the dimensions fundamentally, assuming these are not square, right? Now you'd think it's A transpose times B transpose, but no. Because what happens, first of all, when we do that product, we're deleting that middle dimension, and second, we're flipping everything around. So we actually do B transpose A transpose to make that equivalent, okay? So this is like huge. Do not forget to flip the order of your transpose when you do that. Okay. So that's just 2.1. It's this introduction. These are the rules on the street. When you're doing your matrix algebra, you can do addition, subtraction, multiplication. The concept of dividing doesn't really exist for these. And then transpose. Questions before we dismiss? Okay, what are we having read before class on Monday? Yeah, but which sections? Yes, through chapter 1. And then, okay. You guys are good. You guys are good to go.
So, I want to do something. Yeah, that's